you are. Up above the world so high, like a diamond in the sky. Twinkle, twinkle, little star, how I wonder what you are.
Okay, first of all, stars don't twinkle. The twinkling effect is caused by density variations in the air. Second of all, stars aren't little. Even the smallest is at least the size of Jupiter. Thirdly, the stars we see aren't like diamonds at all. Although, when stars like our sun die, the carbon within them can form very large diamonds indeed. And speaking of gems, this is another story about the women in astronomy, because it was a dedicated group of women in the late 19th century who laid the groundwork for understanding the final riddle of that nursery rhyme, How I Wonder What You Are. Look at this picture of Orion. It's beautiful, isn't it? You should get a pair of binoculars or a telescope and go out one winter's night and just scan around inside of Orion. There are wonders upon wonders to be found inside that constellation, especially in the Sword. But now what I want you to do is look to the upper left. See that bright red star up there in Orion's shoulder? That's Betelgeuse, a red supergiant star that's going to go supernova sometime in the next few thousand years. And now look down at the lower right. See that bright blue star down there in Orion's foot? That's Rigel, a blue supergiant star that's also going to blow itself to hell one day. Look at the difference in the colors of those two stars. One is obviously red, the other is obviously blue. Stars have different colors, and we can classify them based on those colors. If you run the light of a star through a prism or a diffraction grating, you'll get its spectrum. Now here are the spectra of 13 different stars laid out in order of their surface temperatures. The star Rigel has a spectrum that looks like the third from the top. The star Betelgeuse has a spectrum that looks like the one second from the bottom. Now, the first thing you should notice about this lovely array of spectra is this bright swath of color that goes from the blue in the upper left to the red in the lower right. This swath of color shows us the peak wavelength emitted by each of the stars in these spectra. And if you remember our discussion on the blackbody curve, the peak wavelength tells us the temperature of the star. The second thing you should notice in these spectra are the dark absorption lines. There's two over here at the left and another fainter one over here at the right. Those are hydrogen lines. This one is hydrogen alpha, beta, and gamma. These lines are created when electrons of neutral hydrogen atoms absorb photons of very specific frequencies. Ah, the poor hydrogen atom with its one lonely electron. That electron likes to live here at energy level 1 usually. But at the surface of a star, there's enough heat to sometimes kick it up to level 2. And that's interesting to us because the 3 hydrogen lines that we've been talking about correspond to the transition of that electron from level 2 to 3 for the alpha line, 2 to 4 for the beta line, and 2 to 5 for the gamma line. In other words, our 3 hydrogen lines all begin with the electron at level 2. And that explains why the colder stars at the bottom of the chart have faded out lines, because those stars are too cold to get the electron up to level 2. It also explains why those lines disappear in the hot stars at the top of the chart, because those stars are so hot that the electron never comes down to level 2. So the width of these hydrogen lines is an indirect measure of temperature. Of course, in the last half of the 19th century, nobody knew much about this. Astronomers of the day understood that there was a correlation between temperature and color, and they knew the positions of the absorption lines, but they really didn't have any idea why some stars would have such bold absorption lines and others had none at all. The first scientist to classify stars by their spectra was Father Angelo Secchi in 1866. His classification structure was pretty simple. Bright blue and white stars went into class 1, yellow stars went into class 2, and orange and red stars went into class 3. He also noted that certain bright blue-white stars had differences in their absorption lines. So, for example, Rigel and Bellatrix in Orion. So he put them into the Orion subtype of class 1. By 1890, Williamina Fleming had classified over 10,000 stars using a modification of Secchi's system whereby Secchi's divisions were subdivided even further and renamed A through N, where A were blue-white stars and N were red stars. She also created another classification, O, for stars that were dominated by strong emission lines. In 1897, Antonia Mori realized that Secchi's Orion subclass, which Fleming had renamed B, was actually a higher temperature than Fleming's A-class star. She thought that the classification sequence should go in temperature order, so she moved B in front of A. So then, in 1901, Annie Jump Cannon took Fleming's classes and combined many of them, getting rid of some of the ones in the middle. She also took class O and moved it to the beginning, giving us the sequence we know today. Oh, be a fine girl, kiss me. Cannon and her contemporaries strongly felt that this was in order of surface temperature. And though they didn't have the theoretical basis to prove it, their instincts were good, because this is indeed in surface temperature order. These are very hot stars. These are very cool stars. There's another interesting order to these. They're in order of mass. Very massive, very light. So here's that array of spectra again, placed in the OBA fine girl kiss me order. Look at the swath of color that crosses through that spectrum again. That swath and the shape of that swath is very important. It's called the main sequence. Stars on the main sequence are fusing hydrogen in their cores. They have not yet begun to fuse helium. So here once again is Orion the Hunter. You can see the 3 stars in his belt and the sword hanging down. To the upper left is the bright star Betelgeuse. At the lower right is the bright star Rigel at his foot. Follow the belt to the left and you'll see the eye of his faithful dog Sirius, the brightest star in the sky. And go up and to the left from there and you'll see the bright star Procyon. The rightmost 2 stars in the belt, Alnilam and Mintaka, are class O stars. They are both about 700 light-years away. They are so hot that most of their energy is radiated in the ultraviolet. What we see is only a small fraction of light that they emit in the visible band. If we could see into the ultraviolet, these stars would be spectacularly bright. We're lucky to have 2 O stars so close to us. Only about 1 in 3 million stars are class O. They are so massive and hot that they don't live very long. Indeed, these 2 stars are much younger than the dinosaurs, and when they die, which will be soon, they will light up the sky as supernova. Rigel on Orion's right foot and Bellatrix on his right shoulder are class B stars, also very hot, heavy, and short-lived, but cool enough to radiate much more visible light. Rigel is a B8 star, and it's 860 light-years away, whereas Bellatrix is a B2 star, which is just 250 light-years away. They'll also go supernova one day. Now look over to the left at Sirius. Sirius is a class A star. It's the brightest star in the sky, but that's because it's only about 8.6 light-years away. It's much hotter than our sun, but it has nowhere near the luminosity of Rigel. Now look up from Sirius. See the bright star Procyon? Procyon is 11 light years away, not much further than Sirius, but quite a bit fainter. Procyon is a class F star, smaller and cooler than Sirius, but still bigger and hotter than our sun. G stars, like our sun, are pretty small and faint when you put them up against a constellation like Orion. There's really only a handful of visible G-class main sequence stars in the sky, but I can show you one that's pretty well known. Here, in the southern hemisphere, you see the Southern Cross on the right. On the left are Alpha and Beta Centauri. Alpha Centauri is a G-class star, very similar to our sun, maybe a little hotter, maybe a little brighter. It's 4.5 light years away. It's very close. In fact, it's one of the closest stars to the sun, which is why it appears so bright. Main sequence stars that are class K and M are very small and faint, and to see them, you need a good pair of binoculars or a telescope. On the other hand, stars that leave the main sequence often grow into giants or supergiants that are K or M. Betelgeuse is such a star. It's M-class, and it's so large and luminous that we see it as a bright star even though it's 650 light years away. In recent years, our telescopes have gotten so good that we've been able to identify very, very faint and cool stars, and we've classified them as L, T, and Y. These stars are so small, they're maybe the size of Jupiter, and the coolest of them radiate at a temperature that we would consider room temperature. Now you might be wondering how you add L, T, and Y to "Oh, be a fine girl, kiss me." And the answer to that is simple. Lots of tongue, yes. Yes? Lots of tongue? Lots of tongue, yes? Yes, that's right.